Hey guys, today we're going to be doing some really quick hybridization practice, so let's get straight into it. The first compound is given as BeH2, right? So Be, we know that beryllium is going to bond on two sides and hydrogen can only bond on one side. So you should already sort of picture that the structure is going to have beryllium as a central atom and it's going to bond to hydrogen on both sides. So this structure is linear. And in order to calculate the hybridization, we have to consider how many atoms surround beryllium. How many pairs? One pair, two. So there are two effective electron pairs, meaning the hybridization is sp, as in 1, 2. 1, 2. Okay. The next compound will be Te tellurium F4. So tellurium F4, the shape is a little more complicated than just linear. It's actually a seesaw shape, and I will show you how. So here is my tellurium, and when we think of tellurium, you always have to consider the lone pairs of these elements. So here I have a fluorine and a fluorine. Here I have its lone pair, and here I have another fluorine and a fluorine. The reason that you have to consider lone pairs is because you have to consider that every single sort of lone pair on the tellurium is sort of going to split and bond with the fluorine. So if you have 4 fluorines, you can say that 4 are going to, 4 are going to sort of split up and bond to the tellurium, to the fluorines, with of the electrons, and there's going to be remaining, and whatever is remaining is typically the lone pair. So I'm trying to predict the hybridization. So I automatically already know that this is a non-polar molecule, right? This is polar. This is very, 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 very polar, because you have one pair of electrons on one side and then the other side is fluorines. This is polar. They are not the same. So this is a seesaw shape. Seesaw. So I have to consider how many effective pairs are surrounding my tellurium. So I have 1, 2, 3, 4, and I'm done. Nope, that was a trick. I'm not done. I have this lone pair. This lone pair counts as an effective pair. You have to count the lone pair, otherwise your answer will be wrong. And the hybridization becomes DSP3. 1, 2, 3, 4, 5. This is 4 plus the D is 1. And that is your hybridization for TeF4. Okay, now let's do another practice problem. Okay, let's do this one. This one's cool. Let's do SeF6. So sometimes with these problems, I can already visualize what the shape is going to be. I'll give you a minute to think, and then I'll say it. The shape is going to be an octahedral. I know here's my selenium, and I'm going to have 1, 2, 3, 4, 5, 6. F, 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 F. These are sort of connections that when you just practice, you'll start to make right away. I couldn't just make these when I was born. I was like, yeah, this is an octahedral, this is a trigonal planar, this is a square planar, and this is T-shaped. It's not like that. It's practice, and it's truly understanding what the material means. So here are all my electrons around it. Okay, now I know the shape. And if you know the shape and you're good with hybridizations, you'll know automatically what this hybridization is. But I know that this is not polar, right? Not polar. Because every end is the same. Every end is symmetrical. No matter how I flip this molecule, let's say if I was using a physical ball and stick model, the ends will always be the same. So this hybridization, we have to account for everything around the selenium. So 1, 2, 3, 4, 5, 6. So I should have a hybridization that typically has 6 variables. So my hybridization would be D2SP3. 3 plus 1 plus 2 gives you 6. And it has 6 effective pairs.